So before we proceed with this webinar, I'd just like to let you all know that we are recording this so it can be preserved for posterity and reviewed by many other people, including yourselves in the future. Could I ask that you familiarise yourself with the toolbar on the right hand side of your screen? You'll notice that you're not able to join an actual audible chat, but you should be able to pose questions. In the questions area, can someone give me a signal that they can hear me, please? Okay, looks like someone's raised their hand. Yeah, great, thank you, Gary. Okay, I've just realised my battery's not low. Thanks for that. So, welcome to this webinar on functional solutions. My name's Dave Collier. I'm one of the UK training team here, and I'm within Pilz's global services team as well. We're joined today also by my esteemed colleague Dave Scott, who's the UK product manager for Pilz products, some of which we'll be talking about nearer the end of this presentation. Both of us have got access to the questions section. During the webinar, we will attempt to answer questions, and if we can't, we will get back to people shortly after the webinar, because we can record all your questions. So, for those of you that have just joined, just a reminder that we're recording this so we can let you have access to it afterwards if you need to leave for whatever reason during the course of this presentation, which should last for roughly 1 hour. Okay, so the content of today's webinar is broken up into an introduction. There'll be a section where we talk about legislation, so the legal requirements and standards which allow us to comply with those requirements. Then we're going to talk about a couple of applications, so electrolysers, which are used for generating hydrogen, and we'll also be talking about fueling stations. And in both cases, we'll be showcasing how some of the Pilz products can be used to interface with other third-party products to realise safe solutions. Then in section 5, we'll be talking about identification and access management as part of industrial security, which is a growing topic in the world of machine safety and has been a topic in the world of process safety for quite a long time already. And then finally, so, quick introduction. For those of you that don't know Pilz, we are a safety and security expert company. Our core competency is safety, where the protection objective is safety worldwide. So we are present in about 42 countries around the world, and we're probably best known for the components that we manufacture: the safety relays, safety controllers, safety PLCs, various machine safety components that you might find on machines. We have participation in about 50 of the standards committees around the world, so from the IEC to the ISO and the CEN and CENELEC authorised bodies that publish standards. We're involved in the authoring and the maintenance of these. So in the world of hydrogen, there is a supply chain that already exists. So from, if you like, start to finish, hydrogen doesn't exist in its nascent raw state. It's normally combined in other compounds. So the most common of which is water, and hydrogen can be generated at large scale using electrolysers to split water into the two constituent parts, oxygen and hydrogen. The electricity which is used to drive this process can either come from the normal grid or from other renewable sources of energy, such as wind farms and PV, or even hydroelectric. The types of machines that are used for this process are known as electrolysers, and we'll be talking a little bit later about alkaline water and membrane, proton exchange membrane electrolysers. Roughly 10 to 20% of hydrogen today is made by this process, and that's probably overestimating it. The majority of hydrogen today is actually made in what are known as reformers, which basically take methane, react it with steam under high temperature and pressure in the presence of a catalyst to produce hydrogen, to crack, if you like, the methane. But in that process, we also release carbon dioxide, which either escapes into the environment, in which case we refer to the hydrogen as being grey. So it's not exactly green because production is also producing carbon dioxide, or the carbon dioxide can be captured and stored, perhaps underground or combined with other substances, in which case the hydrogen is called blue. This is where carbon capture is involved. And the beauty about electrolysis is that, especially if we're using clean energy process, the products are oxygen and hydrogen, and there is no carbon dioxide, in which case the electrolysers are referred to as being or producing green hydrogen. We then talk about the next step, which is when hydrogen has been generated, it needs to be transported elsewhere. So this can be done, for example, by dissolving it in liquid organic hydrogen compounds, or combining hydrogenating compounds that will store the hydrogen for transport, or maybe pressurizing it and transporting it by truck in cylinders. Sometimes it can even be combined with special metal hydrides. The next challenge with hydrogen is the possibility of being able to store it, and storage normally involves pressurizing it inside cylinders and maybe even dropping it down to as cold as 150 degrees, so it becomes liquefied. One of the applications that more people will become familiar with over time is the need to fuel a vehicle which is either running on a hydrogen internal combustion engine or is using hydrogen fuel cells. And we're going to talk later on about some of the specific challenges relating to refueling and one of the rather unique properties of hydrogen when you release it from under pressure. It doesn't do what you expect it to do. And lastly, obviously, hydrogen is used in other processes other than potentially transport. So there are lots of chemical industries that require hydrogen, for example, in the manufacture of other compounds such as ammonia. And of course, in industry, a lot of hydrogen gets, or other organic combustible materials get burnt, heat, for the release of energy. So we'll talk a bit more about those further down the line. So in terms of safety functionality, over the last few years that Pilz has been involved with clients dealing with hydrogen, we've learned together what are the typical functional safety requirements in each of these applications. So when it comes to the generation of hydrogen, we must be thinking about monitoring certain process parameters in order to keep our process of hydrogen generation under safe control. And this can include monitoring of pressure, temperature, voltage, and current, and also the need to be able to measure gas concentration, as well as detecting any kind of leaks that might occur. Associated with hydrogen generation, obviously the need interaction with it, either to commission it or possibly fault find and do general maintenance, and these areas need to be very carefully managed in terms of security, which is where we would need access management and potential safety gate solutions that keep people out unless they're authorized. As far as transportation is concerned, one of the biggest challenges with hydrogen across the entire supply chain is leakage detection. And on that note, I would just like to point out that Pilz has just recently formed a global partnership with the company Draeger, who manufacture gas detection and gas monitoring systems. And later on, you'll see how some of their equipment can be connected to ours. Another issue with any kind of system where hydrogen is being contained is what we call tightness monitoring. So anyone who's been involved in hydraulics and pneumatics will be familiar with this term. It's all about valves to control the flow or no flow of a fluid, in this case hydrogen, and the way in which we logically drive those solenoid valves one after the other to check that both is working is part of the tightness monitoring. And flow monitoring is also very important. When we come to hydrogen storage, more or less the same variables are important, but particularly pressure, because we must avoid exceeding the pressure of the vessel, which is used for storing the hydrogen. As far as fueling stations are concerned, which we will talk about in more detail nearer the back of this, we need to consider some other traditional human interface safety functions, because people are now involved in the process, such as emergency stop and access management. And pressure monitoring is something I'm going to be honing in on later on, because of the unique property of hydrogen when we depressurize it. When we come to hydrogen consumers, one of the really critical functions is to be able to make sure that we get the gas mixture correct. So the stoichiometric mixture of hydrogen and oxygen is different to that of methane or propane and air. So controlling the mix of those two gases to get an efficient and safe burn is very, very important. Okay, so who's using hydrogen these days? Well, in the UK at least, the government is providing funding under what are called hydrogen allocation rounds, and we're in the second hydrogen allocation round right now. And the report that has come out of that highlights that those who are actively vying for the funding to fulfill the major projects involving hydrogen include the paper industry. A lot of heat is required in the paper industry to dry paper. It's coming off the production line. Transport, obviously, I've recently taken bus rides around Birmingham in hydrogen fuel cell buses, and obviously that means there's a requirement for refueling and for production of hydrogen. And if you visit Tyseley Energy Park in Birmingham, you'll see there are two substantial electrolysers there and a refueling station, one for a bus which runs at 350 bar and one for cars which runs at 700 bar. Refineries obviously always are using hydrogen, and obviously they are going to come under some pressure to be sourcing their hydrogen from greener sources than maybe they have been in the past. The manufacturing of glass is rather similar to paper. There's a requirement for heat in that process. Airports, there are companies that are now looking at using hydrogen as a fuel for aircraft. In fact, recently I saw Rolls-Royce develop gas turbines for their engines for aircraft that run on hydrogen. And in Bristol Airport, there's been a project recently where the tractors that pull the luggage trolleys around are driven by hydrogen fuel cells. Breweries, similar to paper and glass industry, and lime kilns as well, these all require a fuel that they can burn to produce heat, which hydrogen is ideal for. Power producing companies, there's a project that's starting in the east of England where one of the major power producers is going to be using spare electricity from the grid to electrolyze water and then pump the hydrogen deep underground into salt caves, and later on, when there is a high demand on the grid, pump the hydrogen back up from underground, put it through a gas turbine, and produce electricity, which can be used similar in some ways to hydroelectricity, being cooled demand. And then there are many local industries, too many to mention. And the big question is, why are they looking at using hydrogen? And there are two main reasons. One is the big political drive and environmental drive to reduce carbon dioxide emissions, aiming for what we all collectively know as net zero, to reduce our carbon footprint. And then there is a financial side to this, which is that, at least in the UK, the government has implemented what is called a climate change levy, where basically an environmental tax is imposed on businesses that consume electricity and gas as part of the government's fight against climate change, and it's normally paid through the business's energy provider in their monthly electricity and gas bills. So there's an environmental factor to this, but also a very big financial factor. So I've mentioned that hydrogen can be green, but the big question is it? Basically, the hazards associated with handling hydrogen are no less risky than with traditional hydrocarbons, and I would argue vice versa as well. So methane is flammable and can explode in the right concentrations. It needs to be handled carefully. Hydrogen is similar in that regard, but it does have some slightly different properties, which we'll go into in the next slide. But that safety precautions are essential to ensure safe applications, and this topic is going to be affecting not only equipment manufacturers, but the users of that equipment. In my research, I found that there is actually a hydrogen incident and accident database, which has been recording so-called undesired events and lessons learned. You can find it using the links below to the HIAD. This is the industry and accident database. It's currently in version 2.1. It can be found on the Europa Minerva homepage, and it contains quite detailed information about all the incidents and accidents that have been recorded way back, indeed, until the date that the Montpellier brothers developed the first hydrogen lofted balloon. I took the liberty to extract from that database information dating back 10 years to look at how many incidents and accidents have been reported across the world. And this isn't to suggest, for example, that because 56% of those incidents have happened in Europe, Europe happens to be the most dangerous place. I would argue that it means that Europe happens to be the place in the world where hydrogen has been adopted the most. Conversely, in the UK, there have only been 12 recorded incidents, which totals 6% of all of the incidents and accidents. And to me, this suggests that the UK needs to catch up with hydrogen adoption. But what avoid is catching up with the actual incident and accident rate. So, a few fun facts about hydrogen that are relevant to safety. So, I mentioned that I tried to compare methane and hydrogen earlier on. So, in terms of comparing these two, we can say that hydrogen has a greater propensity to ignite, probably than any other gas. It has a very wide flammability range, so that it has a lower explosivity limit of 4% in air, and all the way up to 75% upper explosion limit. So basically, if you have hydrogen mixed with air in that range, it's explosive. And when you compare this with a gas like methane, methane has a much narrower explosivity range or flammability range. Coupled with this, it doesn't take at all hydrogen. It's about 0.17 millijoules compared to 0.28 millijoules for methane. So, you know, the slightest static discharge, for example, is more than likely going to ignite hydrogen gas. And this is why there's quite a focus on the elimination and control of ignition sources, and the application of the principles of the ATEX directive, or directives, I should say, that which is used for the certification of equipment, and also that which is used by the end user to ensure that their application is safe. Another property about hydrogen is that it burns about 400 degrees hotter at 2,200 degrees centigrade than methane. And the flame, it's about 8 times faster than methane. It's an extremely fast flame, and its heat value, or its calorific value per kilogram, is about 3 times that of methane. So it burns very, very hot. And if you are going to be converting an existing methane or other hydrocarbon burner to using hydrogen, it's very important to make sure that the materials of your burner and the chamber and all the other parts that might get hot needs to be carefully assessed to ensure that the hotter spots that might result from a hydrogen flame are not going to damage or dangerously damage the equipment itself. On the subject of the hydrogen flame, it's virtually invisible. If it weren't for impurities that might be getting into the feed, the flame is very, very pale blue. And it is also, all it produces is water when it burns, unlike a hydrocarbon flame, which produces carbon dioxide, sometimes carbon monoxide if it's burning a bit rich. And these carbon containing compounds in a standard hydrocarbon flame mean that they can be fairly simple ionization sensors. When it comes to detecting a hydrogen flame, for example, in a burner, where we need to ensure that the flame hasn't gone out, and if the flame does go out, we shut the safety valve off to stop the supply, an ionization sensor isn't going to work, particularly even if you're mixing methane and hydrogen together. Once you get to about 75% hydrogen, that sensor will not work. So either thermocouples could be used, or more often it would be a combination of ultraviolets or infrared sensors that would be used to detect the hydrogen flame. The hydrogen molecule is very small and very buoyant. It's a very, very light molecule. So coming with this is an elevated possibility of leaks. And if there is a leak, it's going to rise very quickly to any space where it can accumulate. Another factor is that because of the small size, molecule can permeate the inside of the material of a tank or a vessel or pipeline, or indeed any other components that come into contact with it, and cause what is known as embrittlement, especially if the pressure inside that vessel rises and then falls, causing the gas that has managed to permeate the metal, then expands, causing it to gradually start to form cracks. Another thing which can happen with hydrogen at higher temperatures is what is known as hydrogen attack. So these two phenomena are something that the people who are selecting the materials for the hydrogen system need to be aware of. And I've spoken with various valve manufacturers who, for some of their higher pressure, several hundred bar rated systems, actually use special grades of stainless steel, and potentially even use graphene to coat the inside. They protect it from these effects. And of course, if we do get any embrittlement or hydrogen attack, there is also the possibility of leaks occurring. So monitoring is also important here. I alluded earlier to the fact that hydrogen does something which you might not expect, and that is when you store it under pressure and then you depressurize it, for example, in a refueling application, the release of the pressure of the hydrogen causes the gas to warm up rather than cool down, due to what is known as the reverse Joule-Thomson effect. So in a refueling or a filling process where you have a high pressure, say a compressed gas system, from which you're going to feed fuel into another rack or into a vehicle, that rise in temperature needs to be taken into account, more so on the receiving vessel than on the vessel that's doing the filling. The relative pressure and temperature, if any of you did physics, you'll know the equation PV equals nRT. So yeah, as you'll see later on when we talk about refueling systems, this effect is something that needs to be taken into account. Okay, enough about that's the introduction. We're now going to talk about some of the legislation. So the first thing to point out is that there are laws, or what we call regulations and directives, which you'll find in the UK, which is where I believe most of you are based. If not in Europe, we use what are called regulations and directives. So from an equipment point of view, to be able to place a piece of equipment on the market, particularly if it's handling hydrogen, the typical types of directives and regulations that we will be looking at include safety regulation, otherwise known as pressure equipment directive in Europe. I've mentioned ATEX already. So in the UK, equipment for use in potentially explosive atmospheres regs, otherwise known as ATEX directive in Europe. The electromagnetic compatibility regulations in the UK, otherwise known as EMC directive in Europe. The supply of machinery safety regs, so anything that fits the description of a machine will need to comply with this, which currently in Europe is known as the machinery directive, but come January the 20th of 2027 will be known as the EU machinery regulation, and that is going to come with some new requirements that I'll talk about later on regarding security and prevention of corruption. And then, for example, if it's an electrolyser, it will need to meet the requirements of the electrical equipment safety regs, otherwise known as LVD in Europe. So those types of regulations and direct UK assessment marking and CE marking. From an end user point of view, those that are putting the equipment into use are going to need to comply with a number of sets of regulations, most relevant of which would be the Dangerous Substances and Explosive Atmospheres regs, DSEA, otherwise known as ATEX in Europe. In the UK, the Control of Major Accident Hazards, COMAR, known as CIV-ISO 3 in Europe, and generally the Provision and Use of Work Equipment, or PURE regs in the UK, known as the Amended Use of Work Equipment Directive. So this is where all of the essential safety requirements for equipment and for the use of the equipment come. And the way in which we demonstrate compliance with these requirements is through the use of standards and/or guidelines, best practices, and technical reports. So this is not an exhaustive list, but so for electrolysers, the current international standard is ISO 22734, and it contains normative references to other standards that help with the design of said equipment, such as IEC 61511 for functional safety. So this is a process functional safety standard rather than a machinery safety functional safety standard. That also points to IEC 62443 for industrial security of industrial automation control systems, IEC 60204 Part 1 for electrical safety, and the IEC 679 suite of standards for ATEX, and there are many, many more. So that's specifically for electrolysers. There are other standards that are for specific hydrogen applications, such as the ISO 19880 standards for fueling stations and the associated SAE J260 fueling process, which I'll go into in a bit more detail when we talk about fueling applications. And then there is another standard, ISO 26142, which is specifically addressing hydrogen detection apparatus. There may be other standards that are not directly related to hydrogen, which would be necessary to refer to. For example, if using hydrogen in a burner, apart from looking at the particular aspects of hydrogen, you would need to look at the requirements for what is known as thermal processing equipment, the ISO 13577 parts 1, 2, 3 and 4 standards, which I've currently been looking at, helping customers in a different part of the world where they've been converting standard burners to hydrogen burners. Probably the most relevant document for all hydrogen applications, regardless of what the application is actually vehicle reports, ISO TR 15916, which addresses holistically the basic safety of hydrogen systems. It's essential for ensuring safe handling and use of hydrogen across various applications. So it highlights safety concerns, typical hazards and risks associated with hydrogen. It details the properties of hydrogen relevant to safety, some of which I've mentioned on the previous slides, and it provides guidelines for mitigating and controlling hazards and risks. So this is a must-have reference for anybody that's dealing with hydrogen, and I believe that it's being currently reviewed and will be probably in the next year released as a TS, a technical specification, as opposed to a technical report. Specifically in the UK, if you are looking at burners and converting them from typical hydrocarbon to hydrogen, and your is operating greater than 70 kilowatts output, then there is a draft publicly available specification from the BSI called PAS 4445. I have been reading this on and off recently, and it's extremely useful because it talks about some of the very, very specific features of hydrogen that you need to consider in a burner. For example, if you have the nozzle of a burner pointing upwards and you compare that to a nozzle pointing downwards, the flow rate of the hydrogen needs to be adjusted accordingly because of its buoyancy. Okay, if the nozzle is pointing downwards, you need the flow rate to be higher to compensate for the fact that the hydrogen is naturally going to try and flow back up the nozzle because it's so buoyant. Okay, so I've mentioned functional safety and cyber security in the title of this. The gist of it is this: functional safety is all about preventing dangerous conditions from occurring in equipment that might otherwise harm staff, people, the environment, and possibly the equipment. So all of the control systems that are dedicated to maintaining safe states is what we refer to as functional safety. And there's nothing really new in this. It's been around for a very long time. Now, hand in hand, we have to consider security, which is not so much about protecting people and the environment, but it's actually about protecting your machine or your process from accidental or deliberate manipulation by unauthorized access. So the topic of protection against corruption is actually now appearing in the 1230 machinery regulation. So that is going to be the replacement for the machinery directive in January 2027. It's already available to use, and a lot of people are already steering themselves towards using it in readiness for that date. And in Annex 3, which is where the essential safety requirements are listed, there are two specific ESRs, 1.1.9 for protection against corruption, and 1.2.1 very specifically for logging of any attempts that are being made to change the system. And there is currently a draft standard being put together, hopefully will be released at least for vote in June this year. So it's called PREN 50742. And this standard, which is being put together by CEN, is going to be harmonized to those two machinery regulation, and it will become mandatory that designers of equipment conduct an assessment and figure out how they're going to reduce vulnerabilities and, if not eliminate them, and deal with potential threats that might exploit those vulnerabilities. Now, this is new for machinery, but then I should point out, wherever functional safety in a piece of equipment, such as an electrolyser, is referring to IEC 61511, which is the de facto functional safety standard used in low demand process safety applications, there has for a long time been a mandatory requirement to conduct a cybersecurity risk assessment under clause 8.2.4, and the standard that is referred to there is IEC 62443. Specifically, part 3, part 2 of that standard is giving guidance on a security assessment. Okay, so since we're talking about 61511, this is the functional safety standard that is used for determining and engineering and managing the life cycle around safety instrumented systems, where safety functions or SIFs, safety instrumented functions, are there to maintain a safe state. And in the broadest terms, the life cycle in 61511 is a little bit similar to that found in machine functional safety standards, where instead of conducting a risk assessment, we carry out what is known as a process hazard and risk analysis to identify all potential hazards. And specifically, there is a standard, IEC 61182, which details how we can carry out a HAZOP operability study, which I'll talk about a bit more in the next slide. It involves basically breaking a system down into nodes, and at each node we look at a keyword such as temperature or concentration of hydrogen gas, for example, and then we apply a deviation to that guide word, so too much, too little, or none, and then associated with that keyword and the deviation, we identify if there is a consequence or a source of harm, and we can then go about estimating the risk associated with that. We can quantify that. So the HAZOP is an activity that's normally carried out by a team of competent persons that understand both functional safety and how the whole process is designed to operate, so they can identify all the hazards. Now, in any kind of system existing what we call layers of protection. So the second part of this process is to allocate risk reduction to the various independent protection layers that may already be in place. So, for example, the standard control system, otherwise known as the basic process control system, or the BPCS, can be classed as an independent protection layer, giving a certain amount of risk reduction. And there may be other mechanical forms of protection that can be allocated a certain level of risk reduction. So after we've identified a specific hazard, we can then start, and we've quantified the level of risk associated with it, we can then start to quantify how much of the risk is actually being mopped up by those independent protection layers. And in the third stage, we try to quantify this more accurately, either through what's called layer of protection analysis, or through using one of the other methodologies outlined in 61511, such as actually allocate, where necessary, a safety integrity level and a probability of failure on demand of the safety instrumented function that will actually maintain the safe state. So this is, in broad terms, the general flow of how we arrive at determining what a safety instrumented functions safety integrity level needs to be. Now, in the wider context, this life cycle actually appears in 61511 Part 1. It's actually a 4-part standard, but this flow that you can see here comes from the standard, and there are various phases in the life cycle. So we've already mentioned HAZOP, allocation of safety functions to protective layers, and determination of the safety integrity level, for example, using risk-graph or layer of protection analysis. But at that point, we should be able to define the safety system safety requirement specification, which should be the Bible for the next stage, which is designing, engineering, and reviewing the safety instrumented system. Now, before we go into the designing, engineering, and reviewing it, there really ought to be what's called an FSA1. This is a functional safety assessment to check and to verify that all the necessary steps have systematically been followed, so that we are basically mitigating the chance of any kind of human design error. As you'll see in this life cycle, going from design through to install, commission and validation, operation, maintenance, modification and final decommissioning, there are other functional safety audits, whose aim is basically the same as the previous one, just to verify and check that all the necessary requirements from the standard have been met prior to proceeding. And it's functional safety audit, which is one of those things that we're looking to as a service with. And we have already been involved in designing in the design stage using our own equipment. And so this is based on decades of experience, both in the standards bodies and with our equipment and in engineering systems such as these. So the life cycle, I'll just point out one last thing here. I try to think of functional safety like a little puppy dog. It's not for Christmas, it's for life. In other words, if you bring a safety instrument and system into existence, it's not just to design it, install it, fit it and forget it. There needs to be full life cycle structure and planning around it, and functional safety management. So for example, in the operation and maintenance phase, part of FSA4 is going to be an ongoing what we call proof test of all of the safety instrumented functions to check that they are operating correctly, not brought to an as new state, such that they are continuing to provide us with the level of risk reduction that they were designed for. Okay, so enough about safety instrumented systems. Happy to answer any questions about that should anything arise later. So let's have a talk about electrolysers. Okay, so we mentioned electrolysers at the beginning of this webinar as being at the front end of the supply chain. And typical hazards that you could expect to find around an electrolyser could include what we call direct contact. In other words, coming into direct electrical contact with live parts. This is actually something quite relevant, because when an electrolyser stack is installed, it's a large chunk of metal, the output of which depends upon how big it is, but part is not to be grounded to protective earth, because that would affect the actual functioning of the stack. And because the stack, as the name suggests, is made up of a stack of electrochemical cells, it can actually build up quite a large electrical charge on its outer surface. And even when you turn the stack off, it could still present an electrocution hazard, which is defined in 60204 Part 1 as being 60 volts or higher. So we need to prevent that. Okay, so this is a hazard we need to be mindful of. Perhaps more obvious is the risk of explosion and asphyxia if you go into an enclosed space where there may have been a hydrogen leak, where the hydrogen has displaced the air. We also need to think of an electrolyser like any other machine We don't want it to start up unexpectedly. There needs to be a deliberate command, and no faults should cause it to start unexpectedly. And as mentioned previously, someone to it remotely and take control of it if they're not authorized to do so. So some of the mitigations that are available to deal with these include the use of gas detectors, the use of fail-safe ventilation, so the monitoring of ventilation in an enclosed space, and making sure that if we detect hydrogen levels exceeding a certain amount, or before they even get to that level, we can shut down the electrolyzer. We need to think about monitoring of current and voltage, which I will explain shortly, as well as water conductivity. And as far as remote connection is concerned, identification and access management and the use of firewalls or virtual private networks are solutions to consider. So I mentioned earlier the standard for electrolysers, that being ISO 22734. One of the fundamental requirements of this standard, and there are many, is that a single failure of a safety control not cascade a hazardous situation. Seems obvious, doesn't it? The standard then goes on in clause 4.5, if I remember correctly, to list some of the things that need to be monitored or controlled safely, and whose failure to danger needs to be considered. So in the cell stack, which is where the electrolysis takes place, we need to monitor voltage going over or under the maximum and minimum voltages specified by the manufacturer. We need to think about unbalanced voltage, temperature being too high, and current density within the stack. A lot of these values will play part in what I'm going to describe next, which is hydrogen crossover. Cell differential pressure. So this is in, for example, proton exchange membrane electrolysers. Many operate at about 30 bar. If the temperature goes too high, that can also either cause damage or over, which was where we have liquid electrolyte being used. We need to think about the level of it being at the right level, and also whether the flow rate is too low. That could be dangerous if it's too low. Pressure is important. Obviously, we're talking about pressure equipment here, so we need to make sure we don't exceed certain limits, otherwise we might get leaks or worse still, mechanical damage. And the pressure could either be for the hydrogen or the oxygen side. The two gases, when they come out of the electrolyzer, go into tanks, which need to be monitored. And if the hydrogen is going to be then compressed to be stored in another cylinder, we need to monitor that. A critical one is monitoring the fraction volume of hydrogen in air or oxygen in the oxygen line, and it mustn't exceed 2%. 2% is half of the lower explosion limit. And also, we must monitor for the hydrogen size not exceeding 3%. Outside of the stack itself and inside the container that it's located, we need to consider, as I mentioned earlier, continuous ventilation. So there's airflow, akin to local extraction and ventilation in other machines, where we need to make sure that that ventilation is running all the time to prevent an air mixture with hydrogen actually reaching 1%. So obviously we'll have hydrogen detection in the container as well. There's a few other things to consider, such as the overall ambient and process temperature. Where we have concentrated alkaline solutions, we need to think about detecting leaks that might occur over time. The water that is fed into the electrolyzer, depending on the type, needs to be particularly pure, not too many solutes that affect its conductivity, because this can actually damage the membrane in the electrolyzer. We need to make sure switches are, and if limit switches are used, for example, on valves, then they need to be operational and working correctly, and the valve failure must be therefore detectable. And then probably least, we also need always to be able to shut the system down in the event of emergency. So that's a control function that we do not want to lose. So I mentioned hydrogen crossover earlier. This is where basically hydrogen misbehaves and goes the wrong way inside the cell or each cell of the electrolyzer stack. So we sometimes refer to this as anodic hydrogen crossover. So there are more types of electrolyzers than I'm showing you here, but effectively the oldest and most widely used is on the right hand side, alkaline water, which basically uses a concentrated alkaline solution, potentially of potassium hydroxide, and electrodes, cathode and anode, are immersed in this, and the membrane is used to separate the cathode and the anode. Usually it's a diaphragm made of various materials. I think zircon is one of them. And the idea is that that diaphragm basically blocks the hydrogen and the oxygen from mixing with each other. So it acts as a barrier. It also acts as an anion transport mechanism. And as you can see, hydrogen is supposed to form at the cathode and oxygen forms at the anode. And what we want to prevent is the crossover of hydrogen from the cathode to the anode across the diaphragm. Because if it gets over to the oxygen side, we now have a potentially explosive hydrogen-oxygen mix. And to cut a long story short, the same thing could occur in anion exchange membranes, which you see in the middle. The main difference here is that there is no concentration of side. Instead, we have a weak alkaline solution that's being used. The membrane is made of a different material to the diaphragm that's used in an alkaline water electrolyzer, but essentially there is still the possibility that hydrogen could cross over to mix on the anode side. And the same possibly could occur in a proton exchange membrane type of electrolyzer. So there are factors that can be monitored to prevent or detect early signs of this crossover occurring. And I mentioned earlier, cell voltage, stack current density, and differential stack pressure. Those variables all have an effect. So for example, if the stack current density is too high, then that could actually drive hydrogen the wrong way. Stack temperature, the flow rate of the water. The reason the flow rate of the water could be an impact is that when oxygen bubbles, for example, start to form on the oxygen anode, and when the hydrogen starts to form on the cathode side, if the water is not flowing fast enough in either of those two scenarios, we can end up with bubbles actually accumulating on the anode and the cathode, which actually reduces the cooling effect of the water, raising the temperature, potentially damaging the membrane and increasing its permeability and potentially degrading it, causing it to allow hydrogen to cross over or go back the wrong way. So without trying to go into any more kind of chemistry or physics, we have to remember that the lower explosion limit for hydrogen is 4%. So we need to ensure that if the crossover does occur, we actually shut down the stack well before it reaches that concentration, which is why in the standard it mentions shutting down the stack if there is greater than 2% volume of hydrogen found in the oxygen line. Okay, this would be used. So I've talked a lot about the stack and the cell inside the stack, but actually an electrolyzer system is it can look like this. Okay, so the overvoltage undercurrent cutoff, the contact protection that I mentioned earlier, there you can see we've got live connections to it but no earth, and we've got the warning sign on us telling us that it's potentially live and it's shrouded, but we would want to be monitoring that voltage, for example, before we let someone in there. And we obviously need to be monitoring not only the current but the voltage to make sure that the cells are working correctly. And if a HAZOP and a LOPA study is done, it's quite likely that the function of monitoring the voltage and the current may actually be allocated to a SIL 1 or a SIL 2. Okay, so it's our experience having worked on a number of projects where we have been using third-party devices that can monitor current and voltage and provide signals to the inputs of our safety controller for checking the current density of the stack. So we actually monitor the current that is coming out of the DC rectifier that powers the stack, and then we individually monitor the cell voltage, each of the cells in the stack, to check that the voltage levels are correct. So we have sufficient voltage to drive the hydrogen in the right direction, and we don't have too much current that could otherwise cause the same problem. So what you see on the right hand side are devices manufactured by a company called Mutech, and they are SIL rated, and we connect those to our SIL rated inputs on our, in this case, our P&OZ Multi 2, which can actually then be used to monitor what's going on. For example, using voltage monitoring and current monitoring to check what's going on in each of the cells, and we're using dynamic monitoring function blocks in our software to be able to assess that we're operating in the safe limits as specified by the manufacturer. So outside of the stack, there may also be the need to detect or safely detect the presence of leaked gas, and this is where our friends from Draeger come in. They can provide a number of gas detection solutions and even flame detection solutions. I'm no expert in gas detection, but I know someone who is, Megan Hine in the UK, who we work with, and basically hydrogen can be detected either by detecting the molecule itself, or actually listening for the typical high frequency sound that it occurs. So in our experience, most of these field-based instruments, ATEX rated, are out of the box, coming with SIL 2 certification, and depending on the HAZOP and LOPA requirements, you may need to arrive at SIL 3, in which case we would use 2 of these devices and compare their signals in a plausibility block to be able to achieve that. So in this case, it's the 1% threshold that we're looking for. So in this case, if a PEX300 sensor was used, we could use that for producing an alarm if hydrogen is detected at concentrations below 1%. But once that 1% threshold has been reached, then the outputs from our safety controller could be used to safely shut down the stack. This is just, it's only looking at one half of a safety function and one half of it. A typical large electrolyzer might look more like something like this, where we have distributed I/O based around various parts of an electrolyzer system, where we only shut down those parts that are necessary. So here you can see we're monitoring e-stops, feedback from contactors that are used for controlling the stack and the rectifier, hydrogen in oxygen sensing, hydrogen sensors for the local atmosphere, pressure transducers, the flow rate of the electrolyte, airflow monitoring to detect that we've got adequate ventilation in the area of the electrolyzer, water purity monitoring, and pressure switches for that, and also the voltage and current measurements used in the, and the outputs from the system would be typically used for controlling pumps, fans, the rectifier itself, and various valves that are in the pipework. Okay, so another area which I mentioned at the beginning of the webinar was fueling stations. So this is where we're talking about transferring hydrogen gas from one tank to another. So within the supply chain, this movement of hydrogen gas might occur many times before it actually comes to a dispenser to be connected to any form of vehicle, whether it's an industrial type vehicle or a public transport, or earth moving equipment, forklift trucks, trains, aircraft, or indeed cars. So basically you can see here you've got an electrolyzer being a potential source of hydrogen, which would go through stored locally in vertical cylinders. There may be then the need for vehicle transported tube trailers to fill their tanks or their trailers from that local storage. So this is something that happens currently at Tyseley Park in Birmingham. So tube trailers are brought there to top up, and then those tube trailers are taken to, there aren't many in the UK, but we've certainly got experience in France, for example, where one of our customers has a local storage station and a dispenser system, where I've learned quite a bit about the pressure differentials that occur when you're releasing hydrogen from high pressure to low pressure. So it's important that we can safely monitor both the temperature and the pressure gradients on the receiving tank because of that reverse Joule-Thomson effect that I mentioned at the beginning of the webinar. The fact that the hydrogen contributes to the heating process of increasing the pressure inside the receiving vessel purely by the fact that you're releasing the pressure from the feeding vessel. So this is where within our hardware and our software, we can take signals from temperature sensors and pressure sensors and then use differential calculations to be able to safely evaluate that gradient that is time. Now, just showing you this one, it's actually an example where our equipment has been used in one of the tube trailers. It's not actually at a converted petrol station forecourt. We do have an application with a company in France that we can't show you at the moment because we don't have their permission, but if you go onto our website, you'll see animations that depict it. And the point we want to show here is that you don't necessarily need to have a very, for small applications, you don't need a very complicated setup. One of the points that we would make regarding our hardware, if any, is that many of the process signals that you need to monitor safely in hydrogen applications are analog signals, typically 4 to 20 milliamp. Whether you're using our small PNOS multi safety controller or our higher power PSS 4000 safety PLC, a wide range allow us to carry out arithmetic, to do ramp monitoring, gradient monitoring, and threshold monitoring. And in the case of our smaller safety controller, the accuracy or the resolution of this device is actually 1%. It's market leading, and that is relevant because for every % of accuracy in the 4 to 20 milliamp signal, a quantity of gas could be wasted. So if, a 1% accuracy means you can fill tanks up and to greater capacity in a safe way, compared to a sensor that might have a 5% tolerance where you're going to have less latitude. Okay, so just the last thing I want to say about fueling, and I mentioned it earlier, was the reference to this SAE J2601. Currently, when you, or if you go to a hydrogen refueling station, the nozzle that you connect to your vehicle is quite different to the nozzle that you would expect to see if you were using diesel or petrol. It doesn't slot into your vehicle. It actually makes a gas-tight seal by clamping onto the port on your vehicle. And associated with that is an infrared link that establishes a data communication between the vehicle tank and the feeding tank on the forecourt, and it transmits information about the temperature and the pressure of that tank because of the effects that I mentioned earlier. And the fueling protocol, SAE J2601, is all about having a special fueling profile, which involves stopping and starting the fueling process, or controlling the valve, the refueling side, so that we can check that the pressure and temperature stabilize each time the valve is turned off, giving us a profile within which we need to operate. Today, that communication is actually, as you can see here, the communication link from the vehicle tank to the automation controllers of the refueling point is a standard communication. Okay, so that is used for modulating the normal control valve, the non-safety related control valve, and the safety related control valve that would normally be under our control is only controlled by the side by the refueling station itself, which is connected to things like hydrogen leak sensors, flame and smoke detectors, temperature and pressure sensors, and the emergency stop. I mentioned to you earlier that Pilz sits on and contributes to standards committee, and in the future, through the work that's being done within the ISO Technical Committee 197 Working Group 24, it is planned that the data that is coming out of the vehicle over the communication link could actually be brought into the safety controller rather than just the standard control system for the refueler, and that could also be used for safely controlling the flow of the fuel from the refueling station into the vehicle. Okay, so that just gives you some idea of some of the applications that we've been involved in. I have no slides to show to you about burners at the moment, but I've mentioned to you already that we generally apply the ISO 13577 suite of standards to burners and supplement the requirements of those standards with those that come from the technical report 15916. And if the burner's 20 kilowatts, then CAT PAS 4447. So moving away from functional safety, I mentioned the fact that we must consider security and identification and access management. So the requirements for these things come from various sources. I already mentioned the new machinery regulation earlier, and the new essential health and safety requirements for protection against corruption and the safety reliability of controls, and this forthcoming EN 50742 standard. So if any of the equipment that you are dealing with in hydrogen needs to comply to the machinery regulation, you are going to have to address this. If what you're looking at falls under the scope of IEC 61511, then a cybersecurity risk assessment shall be carried out, meaning it must be to identify security vulnerabilities of the safety instrumented system, and that must include measures taken to reduce or reduce the threats that could affect the safety instrumented system. So that's been around for quite a while, and there are now more and more technical reports that provide extra guidance in this field. So what does Pilz have that could help you with these things? And the tall and short of it is that we have for some time been designing and manufacturing components that are certified to the Part 4 of IEC 62443, which is the security standard for industrial automation and control systems, that can be deployed by integrators, builders of equipment, and even end users, should they want to retrofit them, to provide secure access and control of who does what, and also on the right hand side there, you can see a green box. That is our security bridge. It's acting as a virtual private network. So the principles of identification and access management include identifying who is trying to access what piece of hardware or process, and if we can identify who that person is, we can also associate with them what their qualifications are in terms of the necessity of their role and what is their the degree of their education. So we need to identify people and identify their attributes, and based upon being able to identify who they are, how qualified they are, and how educated they are, we can also then allocate permissions to them through the form of some key, and that authorization is something that can be given to them or revoked by controlling the key. Now, in the case of the Pilz solution, that key is actually electronic in nature. Responder, be a physical key or a tag or a card or a tag, and that key, in terms of being able to identify the information on that key, what's associated with it is what we call a reader, or in our case we call it the PIT reader, and a database can be maintained in which we have a list of people who have certain levels of training and knowledge, and the key that they possess contains their data. So only people with the right key can access controls that are associated with the reader. So the PIT reader and the keys that we supply can be configured by the management to associate their people with specific roles and specific level of access. So different areas of use for this could be, for example, if after commissioning and finalizing an electrolyser, parameters should not be adjustable by people who are not qualified to do so. Some of those parameters might be available inside the electrolyser unit on an HMI, and you would only want somebody with the right key to be able to access and do that. Somebody else with a different key might be able to access the HMI, but it won't allow them to modify anything. They may only be able to read things and put the machine into certain modes, such as maintenance, for example. The key can also be associated with a controller or a PLC to activate specific functions, to toggle between different modes, and maybe to set certain recipes. The key could also be used specifically as part of an access management system. So any people with the right key could actually get into a particular area, such as the electrolysers. And if there are particular operating modes that are critical to safety, a key could be used. So associated with a key system, we can also use the other device that I mentioned. So here we have our controller and maybe another controller linked to it over what we call a conduit. And those two controllers, the yellow PNOS multis, are connected to each other and locked behind what we call our safety bridge, the green device. So the safety bridge effectively is treating our safety controllers as living inside one zone, and for anybody to be able to connect to that zone through to either to the TCP/IP port, for example, of our safety controller, they're going to have to go through the security bridge, which is basically a firewall / VPN. And the device, so that you need the password to be able to get through the security bridge before you can actually get into the network to access the safety controllers. There are other features of this device which include digital inputs that locally also need to be made high before anyone can remotely access. And one of those digital inputs, for example, could be associated with that key that I mentioned earlier. So I realise I've gone over the hour, not as much as I normally would have done, and I'm just going to sum up right now. So if you want to know more about functional safety and security around the use of your hydrogen application, even if it's not electrolysers or refueling stations, which I've picked upon today, please reach out to us, because we do have experience, globally speaking, in the application of functional safety and industrial security to these applications. And not only through the deployment of our products, but also through providing our services in training, consulting, and engineering. The last note I'll mention is that if you want to know more about other hydrogen applications where we can help you, please visit Pilz Hydrogen. There's a link on this page here, so it's basically pilz.com/hydrogen. And if you go to our Pilz website, you will also find under podcasts a half-hour podcast on electrolysers. So all that remains for me to say is thank you for attending. There are going to be many other webinars coming on various other subjects, so please visit the pilz.co.uk website, where you will find under the company a webinar channel, so all of our recordings are sent there, and I believe a recording of this webinar shortly after we have finished. So I can see that there is a question in the chat regarding, is it CPD rated? This is not a professionally, it's not CPD rated. This is just a webinar, and if anyone has requested the webinar, our marketing department will be following up on that for you. Any other questions? No? Well, thank you very much, guys and girls. Wishing you a wonderful weekend. If you're in the UK, a wonderful bank holiday weekend, and we'll see you again soon. All the best. Bye now.